We usually think of data privacy as a cybersecurity problem, a digital vault designed to lock away personal information, like passwords and social security numbers. Machine learning changes the mechanics of this protection. Algorithms require massive datasets to train. When engineers feed millions of personal records into these models, the computation yields highly sensitive, unpredictable conclusions known as emergent knowledge. This exposes a widespread misconception in data engineering. Simply stripping up names or hashing ID numbers does not create a truly anonymized or safe dataset. In the age of AI, privacy protection must be treated as a rigorous mathematical design principle, not an optional security add-on. Modern algorithms compute the secrets we never explicitly shared. The 2018 Facebook and Cambridge Analytica scandal provides a clear view into a successful machine learning exploit that weaponized data dimensionality. Cambridge Analytica improperly obtained personal data from approximately 87 million Facebook users without informed consent, using that harvested data to build detailed psychographic profiles. We will now reverse engineer their specific analytics pipeline to map exactly how their systems transformed innocuous digital footprints into precise, targetable vulnerabilities. Understanding this architecture is necessary to engineer future machine learning systems that protect human autonomy. The initial data collection relied on an academic survey application named This Is Your Digital Life. It recruited roughly 270,000 paid participants to take a personality quiz. The critical vulnerability existed in the pre-2015 Facebook API. This programming interface allowed the application to access the data of the participants' entire friend network without those friends ever consenting. This created scale amplification. With an average of 300 connections per user, a small seed of participants cascaded through the network, multiplying into a dataset of 87 million profiles. From this, the application harvested massive volumes of features, including likes and relational connections. The mathematical scale of this cascade transformed a tiny pool of explicit consent into a massive, unconsented behavioral surveillance network. Before analyzing the specific math Cambridge Analytica used, we must examine the underlying mechanism of inference, known in machine learning as the data linkage problem. This chart shows a sanitized medical database containing anonymized patient IDs and prescription histories. Next to it, a second dataset tracks pharmacies and physical locations by zip code. Vulnerability emerges when a model cross-references these isolated sources, calculating relationships between anonymized patients and pharmacies. The algorithm computes where the patient lives by establishing a radius from those zip codes. The raw data never contained a single patient address. The model computed the location from surrounding variables, proving that mathematical correlation can de-anonymize targets. Applying the data linkage principle to the Cambridge Analytica pipeline reveals how they linked Facebook behavior to psychological reality. They achieved this by establishing a ground truth. This ground truth came from the Ocean model, which measures openness, conscientiousness, extroversion, agreeableness, and neuroticism. The original 270,000 survey users established their psychological baselines by answering questions using a Likert scale. Those survey answers served as the labeled training data required for supervised machine learning. Supervised machine learning is a method where an algorithm is trained on input-output pairs to learn a mapping function that can predict future outputs. This diagram shows the feature engineering phase. The model converted each user's digital footprint into a mathematical vector, X, containing likes and posts. In the psychographic modeling phase, the algorithm maps inputs to psychological traits. The model learns to predict a user's ocean traits, the Y factor, based on digital exhaust. This analytics pipeline transformed vague social media activity into a structured, predictive psychological map of the human mind. Once trained, the firm unleashed this predictive model onto the remaining 87 million unconsented profiles in their database. This chart shows predictive thresholds discovered by researchers. Analyzing 68 Facebook likes could predict skin color, and 88 likes determined sexual orientation. With 150 tracked likes, the algorithm predicted personality traits better than a close friend. By calculating these patterns, the model bypassed standard privacy barriers. Human vulnerability proved to be an emergent property that can be calculated strictly from high-dimensional data. The final step was to weaponize these computed profiles for political campaigns, deployed during the 2016 U.S. presidential election and the Brexit referendum. The firm used voter segmentation, where the algorithm sorted millions of citizens into specific psychological buckets. By identifying clusters like high neuroticism and low openness, they mapped exactly where a population was emotionally sensitive. The campaign abandoned mass communication in favor of micro-targeted messaging, carefully calibrated to exploit specific emotional triggers. An individual flagged for high neuroticism received threat-based messaging about local crime rates. Meanwhile, a neighbor with a different psychological profile received an advertisement emphasizing economic opportunity. These were dark ads, personalized digital messages visible only to the specific target. Because they were hidden from the broader public, they were unverifiable by fact-checkers and impossible to debate collectively. The use of AI to personalize reality itself allowed the campaign to exploit specific psychological vulnerabilities at an individual level. Delivering customized realities fragments public discourse and erodes the shared factual basis necessary for debate in democratic institutions. The exploit leveraged a massive power asymmetry between the platform and the citizen, relying on the secondary use of data for unintended purposes and a total lack of transparency. These events motivated the current frameworks for responsible AI, including GDPR, strict rules for purpose limitation, and the demand for algorithmic accountability and explainable AI. Explainable AI is a set of processes and methods that allows human users to comprehend and trust the results created by machine learning algorithms. Attempting to anonymize data by removing names or identification numbers is mathematically useless against modern machine learning architectures. Because computation is inference, true privacy protection requires engineering fairness, explicit consent, and strict purpose limitation directly into the mathematical foundation of algorithmic systems.